G'day, I'm Neil and my handle is Wiley11. I'm just going to put my disclaimer here. Whatever I do and say on these videos is well-intentioned and well-meaning advice. I accept no liabilities whatsoever for any disclosures. If you take some advice or act on something that I'm saying on these videos, you do so entirely at your own risk. I'm doing it based on my experience. These videos are my attempt to give back to YouTube for the help and assistance that YouTube has given me. So once again, you follow along or follow advice from these videos entirely at your own risk. Okay, and if you're not happy to do that, click this off and off you go. Because this is purely my attempt to give back to YouTube, as I said, for the help and advice that I have received out of YouTube. So this is just my little attempt to give back. If you're happy to follow along at your own risk, buckle up, sit in. Let's get into it. Warning t-shirt on because I'm pretty grumpy. I got 3 weeks of work chasing rabbits down rabbit holes. Because when you listen to other people's comments and you read work of people that really know what they're talking about, you expect that you get the picture that you can follow. Now, what I'm trying to do is understand the Watchdog Timer a little bit better, because my understanding of the Watchdog Timer is that it wakes up your processor after it sleeps. But it does way more than that. There's 2 sides to the Watchdog Timer, and as I read through some of the that's too loud. As I read through some of the work done by other people who have used these things a lot, they have a lot of assumed knowledge in what they tell you, which can mislead you. So I've been misled. I've been looking at this Watchdog Timer and I was led to believe that it resets your processor. It counts down from a number, and if you don't reset it or clear it, during your program's operation, it'll completely reset the chip. And it does that. It actually does. But it has 2 modes. It has a normal operation mode, and then it has a sleep mode. And none of these guys talked about the sleep mode. They all talked about normal operation mode. So I started researching this and doing more and more work on it and understanding more and more. And then I suddenly was convinced that I couldn't use this Watchdog Timer to achieve our goal of putting the processor to sleep and waking it up again. It's pretty shit when you think you've got something that you understand. Now, I've only ever used the Watchdog Timer from sleep mode, and I know that it wakes the processor up, and I know that my processor continued from where it left off. So I couldn't reconcile this with what people were telling me, and maybe what I was doing was fluking it. Maybe what I was doing was running my spot, turning the processor to sleep, and then the amount of time it takes for the thing to reset itself comes back online and gives me my PWM at the correct values. And so then I was like, well, this isn't working like that. It's not doing what my expectation of it is. And suddenly I was confused, and I'm down this rabbit hole. And I'm chasing information, more information. And the more I read, the more confused I got. So I'm in my grumpy shirt, grumpy in 3, 2, 1. I'm very grumpy, because I know I wasted a bunch of time. But I didn't really waste it. I came to understand something about the Watchdog. And the Watchdog is this. In normal operation, if you activate it in normal operation, enable it, it starts to count down. So if somewhere up in your code you enable the Watchdog Timer, right? So when you're doing all your setups and declares, you enable it. And you go, yep, okay. And it starts counting down from 256 in a cycle. Now, if you don't reset it, it'll count down to 0 and reset your chip. That's what will happen to it in normal operation. But if you do a clear WDT and then do a set WDT, it resets it. And then if you put your thing to sleep, what it'll do is it'll count down in sleep mode until it expires and then wake the processor up from where it left off. So it's got these two modes. And that's not entirely clear when you read through everyone's work. Everyone kind of assumes you know that. Well, I didn't. I didn't realise there were two modes. And of course, I got into it and I ended up in a world of confusion. Now, the trick to it is go back to the data. If you're really confused, which I was, go back to the data sheet, right? And in the data sheet, you will find all of the answers you will ever want. Now, some of the things I was considering is, do we need to even put this thing to, what kind of advantage are we getting from putting our processor to sleep? And there are some significant gains from putting in terms of power consumption, and we're going to talk about those in this version, in this part 4 of our plan. We still haven't written our program. We kind of put a framework together, and we kind of showed you where we want to go, but we're actually going to show you the design of the circuit for our test circuit. And we're going to show you, once we've got our test circuit built, and I've already built mine, and I'm going to warn you right now, I'm going to show you how to build up this test circuit with our LED to show us our PWM. And we're going to be able to change the programming around and just run it in that holder, in this arrangement, in run mode, and it'll actually work this little LED here. And it'll blink it, and if we change the frequency, we should see it change the frequency. So if we change it to 2 Hertz, it should blink twice a second. If we change it right up to 50 Hertz, it should start that up to a point where we can't notice where it blinks. It'll just appear like a constant light. And then we'll change the duty cycle, so we might change it from 10% right through to 90% at 50, and we should see a brighter and brighter light. That's what we should notice. So that's our expectation, and we know what we want to achieve. And I'm assuming you guys would know that if you increase the amount of power in something, it gets brighter, right? By increasing the active duty cycle, there's more power, and if there's more power, things are brighter. So by dimming it, by shrinking the active duty cycle, it gets dim. If we increase it, it'll put out more power, but it'll also consume more. Just excuse me for a minute. I've been going off of different chips, and not everything that you read is about your 12F675, right? But here, let's have a look at the low power features. So here it is, operating current, right? And let's assume it goes to the maximum at 1 megahertz, 2 volt. Well, we're operating at 3.3 volt, but 100 microamps, typical. Now, when we activate a Watchdog Timer, that drops to just 300 nanoamps. So there is a significant power saving. Significant power saving there. We're going from UA from microamp down into the nanoamp. That's huge. It's a huge amount. So definitely, that tells us that you gain a significant advantage out of putting the thing into sleep mode. Now let's go somewhere else for a sec. And what I found on page 66 of this data sheet is this. Let's go to the original. Let's go to page 66. Right, here it is. Right, this is it here. During normal operation, a timeout generates a device reset. If the device is in sleep mode, a timeout causes it to wake up and continue with normal operation. So that kind of flies in the face of everything that I read in the last week about the Watchdog Timer. This particular chip says right here, if the device is in sleep mode, the Watchdog Timer wakes it up and continues with normal operation. So it goes back to the place in the stack. So it just continues executing whatever's on. So it doesn't lose the stack. It doesn't do a complete chip reset. So what you want to do is you want to clear the Watchdog Timer to reset it regularly in your main program. So you can enable it, that's fine. So it can be operating and operating and operating, okay? And all you got to do is run a clear WDT. I think there might be one here somewhere. Yeah. And sleep instructions, clear the, so as soon as you put it to sleep, it clears the WDT and the prescaler. So whatever it's up to, it cleans it out. So using it in this way, this chip gives us a significant low power advantage. Putting the chip into sleep mode doesn't do anything to your outputs, according to this. It just continues normal operation. Now, we can test that as well. We don't have to go to what I was saying before. We can see that we're going to get a significant power advantage out of using this. It's huge. It's 300 times more current draw here than it is here, roughly. 1 UN is 1,000 of these guys. So it's, give or take 30. It's roughly a third. So 300 times more power draw than not using it. Now that is significant. So we're definitely, our thinking is right. I've gotten so confused with this whole thing over time that I've changed direction so many times. So I think we can just forget everything that we just saw, and I'm going back to plan A. So we've still got this issue of being able to program the hertz, the frequency. So we want to be able to plug a frequency in at the top of our code and have it come up with the correct Watchdog Timer setting based on that frequency. Now, I think we can run it from like 1 second intervals right up to 50 hertz. So we're going to have 1 hertz up to 50 hertz as our limiting. I don't think I want to go more than 20 milliseconds. I mean, I could take it up to 500 hertz, but I can't see that you would, you can change that yourself. Once you see the method, you can go ahead and make your own changes to make that happen. So it's going to be about converting the hertz to time active versus time passive. That's what it's going to be, and equating time active to some sleep cycle of the prescaler. So if we want 2 microseconds, that's going to be 500 hertz, right? It's going to blink 500 times a second. Is that right? Yes, it is. It's going to blink 500 times a second. So it's actually going to blink 250 times a second because it's going to be on and then off. So on for 2 microseconds, off for 2 microseconds. So if we wanted 500 hertz, we'd be using the prescaler at its base point. So it's in default it would blink 500. It would blink on and off 500 times. So it would be 250 times 250 hertz is the default position. So we could go very easily from 0 to 250 without too much trouble. We could actually go right up to 2.3, blink once every 2.3 seconds, in which case we would be dropping down from less than 1 hertz, be 0.5 of a hertz, 0.5 hertz. Why you'd want to do that, I don't know, but you might want to. So you can have it in half a hertz or a quarter of a hertz probably. I don't know what that equates to the 2.3 maximum. But even then you could come up with any figure you want based on how many seconds you want it on and off. You just have to keep cycling the watchdog to put the thing back so it'd wake up, go back to sleep, wake up, go back to sleep, until it gets to the desired point. We want to test the output on our pins, so we want to make sure that if we put the thing into sleep mode that our output doesn't stop. So we might just write a simple program to do that test, and we'll do that in this particular, we can do that very quickly. So we can actually set up an output on GPIO 0, then put the processor to sleep, and just have it do a no op. So we'll set the output somewhere in the setup area outside of our main loop. So we'll have that output going, and then we'll have a main loop that says do nothing, do nothing. So you should see it come on, the thing will go to sleep, and it'll do nothing. It'll be completely asleep, but the output will continue. Okay, that's what we want to see. So we can do that pretty quickly. We'll do that probably next. That'll be our next thing. If you haven't built this, you need to now pause the video and go away and build that. Right? And BlinkLock and Arduino has this as well. If you've got my series on BlinkLock and Arduino, you should be able to get that built. There's nothing dramatic about that. There's not that much soldering. There's only a few wires. That chip holder might confuse the crap out of you. It's a dirty great big thing, but the circuit board is only really small. And if all you've got's like a chip standoff, like an 8-pin standoff, well then just use that. You don't have to use a removable chip holder like I had this lying around. But I've had the boards where I've just used an IC holder in a board where you have to pop the chip out with a screwdriver or something. But I find you bend the pins on your chips when you use these, and these are way more convenient. Right, so that's where we're up to. Excuse me, I'm a little bit flustered and whatever else. I lost a lot of direction. I delayed this for 3 weeks and I went away. But at the end of it, I've done 3 weeks of farting around and getting frustrated by well-meaning, well-intentioned people. None of whom were helping me. They were just confusing the living crap out of me. If you ask a forum, how do I just go onto the data sheet? How do I just trusted my instincts and just gone, no, let's just go to a data sheet. It was sitting right there. There were 3 little bits of information, and if I just trusted that, I would have not wasted all that time doing all that research and listening to these other guys, who were talking about active duty cycle, which is completely wrong for our application. Because we're not active, we're in sleep, we're putting the thing into sleep mode. So we're using the other side of the function of the watchdog. So if you got nothing else out of this series, bear in mind that watchdog timers have 2 functions. They have an active mode function and they have a sleep mode function, right? And if you understand that and you take that away from this, well then you've learned something. If you already knew that and you're calling me an idiot, well, more power to you, mate. I just only ever used this thing in sleep mode. That's all the only time I've ever used. I couldn't understand why you would want a watchdog in active mode until I read a little bit deeper into chip failure. Now, there was a rocket. They sent it an instruction to stop firing so that the guidance thing would work correctly, and unfortunately the thing didn't stop. it kept firing and turned the rocket upside down and plummeted it back to Earth. But had they used the Watchdog reset thing, what had happened was the chip overheated and froze, right? Now, had they used the Watchdog thing, it would have shut the chip off and reset it, and they would have recovered the rocket. And a couple of $1 million of rocket would have gone where it was supposed to go instead of going back to Earth and kabooming. So that's the sort of time when the Watchdog is really, really useful. And you know, I only got that out of reading all of that stuff, so I couldn't see why it'd be useful to use it in active mode until I read that, and I thought, well, yeah, okay, I understand that now. You got to think about fail-safes whenever you build something. You got to think about fail-safes. What would happen if that fail-safe didn't happen? And bear in mind, our Watchdog Timer is active. So if our chip freezes in active mode, if it happens to freeze up while it's setting a value or whatever, it would freeze, and then that Watchdog would count down and reset our chip. So our chip would continue to function. Really cool. And we didn't even design that. We didn't do anything with that. All it did was, but we've got to be aware that that's counting down when our chip's active, right? So if we haven't got enough cycles, like if our instruction cycles, like if it kills beyond the period the WDT period is there and our instruction set is there to execute, the chip's going to reset and not execute our instruction set. It's just going to keep resetting. Now, this is why people get so confused when using their Watchdog Timer. It took me 2 weeks of reading through all the crap to work that out. But now I understand it. I understand it pretty well. Okay, let's move forward. About is programming our oh gee, where am I? Oh goodness me, I'm really, there's some more current specifications if ever you want to see it. And again, you know, 300 milliamps, that's not bad. 300 milliamps is pretty good performance. Alright, so what we need to do is get the programming wiring. Oh, I'm in the wrong data sheet. I am in the wrong data sheet. Give me a second. I am looking for the picket. Pause. Sorry. Alright, so we're recording again. Sorry about the mix-up. I'm going to ignore the camera for the minute. Let's get everything out of our road. And what we're doing is we're looking at the user's guide for the picket, because in here there's a very helpful output diagram for the wiring. So this tells you what the ports are. There's your legend. Just in case you needed confirmation of it. What I'm looking for is the outputs, typical wiring. Whoa. Notes. Okay. So this is their output circuit. Here it is. So VPP is 1, so that's actually going to, and this is a microcontroller device. So this is our PIC, and you can see it's on pin 4. And then typically they want you to put a isolation circuit in to give it its separate power supply, but I'm worried about this. I'm not doing that. So what I've done instead of that is I've done an isolation resistor between pins 1 and 4. And so I've adopted this, right, and we've actually got these outputs here. And you can see you've got, well, this is a typical application circuit. And then they go on to describe the pins, etc., etc. So what we're doing is we're taking the information in this circuit diagram and we're building our own. So I'm just going to put that to one side and we're going to go to our application. And we are going to open our test circuit. And you can see here, this is the circuit that I designed to build this board, which you've already seen. So there's the board. It's just a chip holder that I've had lying around. I didn't need to make it that big, but it was the one I had. And that's how I've connected it up with a 10K isolation current resistor between reference and VCC. So VCC, the 5 volt out pin is coming in there, which actually, this is pin 1, pin 2, pin 3, pin 4, pin 5, and pin 6 on the picket as you look at it, with pin 1 being where the arrow is. So there are your 6 pins. Here they are. And we go, and if you follow that circuit diagram, which I'm posting a link to in the project data, in the project documents, I'll give you that diagram. I built this one. It doesn't have to be as convoluted as this one, but this is the only chip holder I could find, so that's how I built it. But at the back of it you can see I've literally followed that circuit diagram to hook up my pins. So it's pretty easily done. QED. There's my 10K resistor there. There's my output, that's my output LED. And it has the added advantage that's on the TX line for programming, so that'll blink quite nicely when it's programming the chip. So you know that data is flowing between your picket and your chip. So that's quite a nice board. You can use it to program your chips as well. So it's got more purposes than just this particular test application, but it's a good thing to have. So we're adopting that, and that's going to be our test platform, and we're ready to rock and roll. So once you've built that, now if you go to my Blink Like an Arduino series, you'll actually see me building that up. I actually have done this, and actually I've programmed the Blink Like an Arduino correctly. So I actually have used the Watchdog Timer correctly. I just haven't programmed duty cycles and blink cycles correctly. I want to be able to modify them. Video part 3, we actually quickly and crudely put this application together, and you can see here we have quite a lot of bits in here that basically follow our flowchart. What we want to do is design a quick little nasty flowchart. So I'm just going to put this to one side. We're going to go back to our flowchart. I'm going to delete that. I'm going to delete all this. We're going to go there. Right. We're going to do that. We're going to do that. Okay, so we're going to do a do nothing. Delete, delete. Group, thank you. Control C, Control V, test 2, we'll have over here. And we're going to set the output to low. Right. Now there we go. We got ourselves a working test. Now what we're going to do is program this. And what we're going to do is we're going to borrow this program here. Is changed when the processor enters sleep mode. There we go. Cool. Alright, so something's happened here. We've got something going on somewhere out here. Can't see it going anywhere out to the right. Use at your own risk, blah blah blah, that's all good. We don't need frequency duty, we do need a PWM out. We're not going to change this. So we don't need that. We don't need all this. We're going to output our constant. So at about this point, even I got bored watching myself type while I was editing. So what I'm going to do is spare you watching me type, and I'm going to flick forwards to a result. But essentially what I did was grab the blink like an Arduino code and put, hack it into our quick and nasty application. Oh, I give up. Alright, so we're doing this one where we're setting it high, sleeping, do nothing, and going around. Alright, so that's the one we're doing. We've set it to max it out. I think it's 5, it might be 4. If we get an error at 5, we'll drop that back to 4. We should be good to go. We should be able to compile this. It's compiling. Build succeeded, so it compiled just fine. So now we should be able to plug in our device and see what happens. Now if you've never plugged your device in before to Microlabs, you'll need to do some setup. I've done this before. Blink like an Arduino, I'll put a link down below, it does this quite nicely. But you'll see I've just connected it. It should say it's got it. Here it is. you can see this is all lit up like a Christmas tree, but we can go into project, programmer, and we're going to select the picket 3, and here it is. It's detected it, it's running things. We're going to say OK, and what we're now going to do is, okay, it doesn't like something, we need to reset it. Sometimes you've got to do this a few times with your chip. I removed it and plugged it back in. You'll notice this is up here. It really doesn't like it. Alright, so let's just go to settings here and check our power. It's set to 5 volts. We don't really need 5 volts. We can go backwards a bit. And we're going to say use that and hit OK and OK. So now our power things are on. I'm going to turn it off. And I'm going to turn it back on. And now it's happy. So we're going to program. We're going to build all. Let's build all. So there's our build, and we're going to program the chip. Here we go. In the script, and got us a working result where if I provide some power to this thing, just opening up microchip. I'm not sure which way project, come on. Project, open, test. Okay. Right, we did provide power through the chip, and you can see that chip's asleep. That chip has been put to sleep and our light's still on. So that is now in sleep mode as per our program. It's running around in circles, putting the chip back to sleep at the longest cycle of 2.3, every 2.3 seconds. That chip's waking up and going back to sleep. And our light is not flickering or flickering or flickering or whatever. I can do it every 50 seconds or 50 milliseconds or whatever, even 18 milliseconds. And we've still got ourselves a light. That's pretty cool. So the outputs are not impacted by the chip being in sleep mode. I did say to you I was going to create a spreadsheet. Here's our spreadsheet in Excel. You can use whatever spreadsheet you like, it doesn't matter. But I'm going to release this anyway. And what I've done is I've done some calculations to understand the Watchdog Timer. Now down here I've got a lookup table just to give me a conversion table from frequency to period, right? So whatever period we have, if we've got 1 hertz, we've got 1 second, 1000 milliseconds, right? So as you can see, as we go down this table, the numbers get closer and closer and closer, right, until we hit 105, and then suddenly we start to see some duplications, right? You've got to remember these are milliseconds, so now these are in microseconds. So down here at 107 hertz, you can see we're starting to duplicate this. They're getting too close together, right? We're getting, and you could go on and on and on, you could get right down the table to, you know, into kilohertz, megahertz, etc. And you could just build this formula. And here's the formula. It's easy. It's 1000 divided by whatever number you want, right? So you don't have to actually build this. You can calculate it. And indeed, that's what we do. So at 15 hertz, right? At 15 hertz, we get 66.7. So I actually did it as a lookup. Well, I don't know why I did that, but I wanted to understand this. But I could have put this formula here into here, and in fact I might just do that. I'm just going to convert this to this, and it's not, it's E16. Right, and I don't want that decimal place. I don't care. For our application, I don't care. 67 milliseconds is enough. Alright, so our period becomes 67 milliseconds at a 40% duty cycle. We've got 27 milliseconds active and 40 milliseconds passive. So that's the square wave duty cycle at 40% active. So then we've got to understand our watchdog, and here's our prescaler over here. Now it's an 8-bit, so it's 2 to the 0, 2 to the first, right? So this is what it translates to in terms of cycles. At 2 to the 0 is 1 cycle. At 2 to the first, it's 2 cycles, 4, 8, 16, 32, 64, and 128. So this is what it translates to in milliseconds, and this came straight out of the data sheet. So if I go back here and I get my data sheet, which I actually had open, here they are here. You can see the WDT rate is straight out of the data sheet, 2 to the first, blah, 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 blah. Now, somewhere close by, not far away from this, I got the period. It's a fair way away. Hang on. Just give me a second. I'm just going to find it. Okay. Next. WDT, here it is. This is exactly the information data sheet. Here it is. It's 18 milliseconds. Here it is. So one pulse, one period is 18 milliseconds, which means it times out over 18 milliseconds unless you use the prescaler. And this is what this tells you. If you want to use your prescaler, you can get up to 128 divisions of 18. So you just multiply that out. 128 by 18 will give you 2,300 milliseconds, or a maximum of 2.3 seconds. And that's what our spreadsheet does. We just multiply. G'day, welcome back. Well, I've done some calculations and I've done a bit more research since I last got on. Still wearing my grumpy t-shirt, and I'm grumpy because I've run up against some limitations of the choices we've made. The researchers confirmed that we've got some issues, and this is the cause of the frustration of the last couple of weeks. So let's get into why we've got some limitations. Alright, let's swap cameras. Multiply this by this value. Here's our 18 milliseconds, here's our 18, right? So these are the milliseconds we get. So one cycle becomes 18, 2 cycles becomes 36, 4 cycles becomes 72. Now these are the cycles here, right? So 2 to the equals the cycles. Here they are, and here are the milliseconds in here. So then it becomes pretty simple. This is just a calculation. So here we look up 27, right? And 27 is 18 with a remainder of 9. Right? So you could use one cycle of the WDT here to give you your 40%, and down here you're actually using 2 cycles of the WDT and a remainder of 4. So this remainder here, it might be more appropriate to use 36, because you'd have an overage of, oh, I don't know, can't do it in my head. I should be able to. It's the same number, because it's exactly halfway between them. But if we change our hertz requirement, let's go up to some numbers where we start to have problems. Let's go to 50 hertz, and straight away we've got problems, right? Because there are no numbers in our table where we can meet that requirement. What that tells us is that our WTT can't do the job at 50 hertz. Why? Because we need, at a 50% cycle, we need 10 milliseconds. And over here we got 18. Right? 18 is our lowest cycle. So right here at this specification of 50% at 50 hertz, our chip can't do the job. But if we change that to 60%, 70%, what I'm doing is sweeping the result. Let's try 80. No, 90% duty cycle. Okay. At a 10%, we can do it because we've only got a 2 millisecond outage where we can't do it. So the power draw for that 2 milliseconds means that we don't put the chip to sleep. Right? So we can actually do the job at a 90% duty cycle. We can't do it at 50%, but we can do it at 90% with the Watchdog Timer. Now that's significant, right? That is significant, because there are some applications where we could use our chip, and there are other applications where we can't. Not without external hardware such as a real-time clock. If we had a real-time clock, all of this is achievable. All of this goes out the window, because if our prescaler is 0.000 and 020, if that's our 20 microseconds instead of milliseconds, now everything's available to us, right? We can even do it we can do it anywhere. Suddenly our numbers are right to rock, because our biggest delay is 2.56 seconds. Milliseconds, excuse me. These are milliseconds, remember? So 2 microseconds suddenly everything's in reach, and we can even get this 15, right? We can get that. We can fine-tune these numbers. We can do setting 1, setting 2, setting 3. We can actually take this remainder and look it up. We can fine-tune it. And our lookup value becomes F21. I think I screwed this up. I gave one too many of them. Might be 200 milliseconds. There it is. So these are the equivalent hertz out here. Pretty sure I hard coded this. I did. I didn't make it a formula. At our prescaler, these are the hertz available to us. Right? So it's actually timing at 55 hertz, roughly. Now we're back to not being able to do any of this. Alright, we've got ourselves something that helps us to understand our 8-bit WDT. This is what this was designed to do. It wasn't really designed to sweep values and do all that, but we can start to plug in some numbers, right? You know, like if we have an external clock, then we can change this value, and suddenly these numbers are achievable with the current hardware with an external clock. You know, an RTC, a real-time clock, will get us there, and we can still use the hardware we've chosen. Or we can swap out the 12F675 for one of the 16 bits, right? If we go to a 16-bit chip, those clock cycles will come down. There's 32-bit chips as well, so we just choose a different pick with a different parameter in here. Of course, I'd have to change this to an actual formula. Yeah, but you see what I'm saying. As the milliseconds get smaller and smaller and smaller, you can see these hertz. These are the actual hertz at which your chip's processing in sleep mode. Okay. So you could keep this going right down to 500 hertz. Let's say we want 500 hertz. So now we've got 2 milliseconds, which is 2,000 ticks of a real-time clock, because they tick over in microseconds, right? So we got, you know, 2,000 ticks. We can do a lot in 2,000 ticks. And your process. Right, so just to wrap up what we've discovered in this, in our research, we've verified that our chip is not good for frequencies in hertz. It's okay for RPM. Our chip is great for RPM. That's fine, because 3000 RPM is 50 hertz, right? So at low RPM, Like if you only want to get 600 RPM, well, you only need 10 Hertz, right? So our chip can do 10 Hertz. It can do that. It can't do 50 Hertz, which is 3000 RPM successfully, unless you've got 100% duty cycle, in which case, you know, you're going full bore on the chip. You don't need to use the timer for that. You know, you don't shut the chip down because you've got power going all the time. But you are creating a square wave at 50 Hertz. Oh boy, yeah, it's getting complicated. So we've run up against the limitations of the chip. We're going to change tack with our software. We're going to keep pressing forward, but we're going to aim for a 10 Hertz PWM. Okay. We might see if we can make it work for 20, but we might land somewhere at around 15 or 18, depending on where the numbers take us. And we're going to stick to just a straight 50% duty cycle. We're not going to vary that. I don't see a point with our code at the moment in doing any of that. Our goal was to output our PWM, you know. So this was our goal, righty, and we can still do that with our chip. And we know that we're limited to extremely low frequency, and we know and understand that our WDT is doing what we need it to do. So that's what, you know, part 3 and part 4. We've designed our tool in this part, which was very, very useful. We know that we can take that tool and modify that for a different project, which I think will build on this project into a new project where we look for a high frequency chip and we work with that. But for the moment, all I've got is the 12F675. So what we've done is we've explained the PWM, and now we're going to get back into the code. We're going to jump in because now we know what we're trying to do. And we're going to cut down on what we're trying to achieve. We're literally going to change our description at the top. We're going to change direction, and we're going to work within the limits of the chip. So let's do that, and I'll see you guys for part 5. So if you liked what you saw, please like the video, subscribe to the channel. Don't forget to support my company, nightglowmanufacturing.com. So that I can keep making these videos. I want you to make good decisions, do good things, and, you know, let's all get along. Let's you know, make life a lot easier for everyone when we all get along. And I'll see you guys at the next video.